Peter Davies is from Tyler's UK. He's the Director of Security Concepts. As a Technical Director of Tyler's in the UK, Peter has been their leading expert on cryptography in the UK, responsible for providing cryptography and information security direction and expertise in a variety of products and projects. Peter's specialist knowledge is at the core of the cyber defence and forensics activity that he undertakes, combating his existential threats against the business. Peter has generated patents in the area of digital DNA, and his research covers aspects of technical security as well as aspects of super identities and their role in combating human-based cyber attacks. As well as contributing to standards, Peter is a frequent speaker at international conferences and delivers lectures to postgraduate information and cybersecurity programs in the UK and worldwide. I think that's everything. The title of his talk is Security, the Enemy of Verification.
That's good, because that's what it says up there as well. Sort of a plan coming together, that one, isn't it? Good afternoon. It says, I'll run through that quickly. In fact, I've run through that, so we don't need to do that one. It's just there so you can read it. This is what I'm going to talk about, or as far as possible what I'm going to talk about. Basically taking the view that security mechanisms are increasingly fundamental to delivering digital solutions of any sort. So it was fine when we were all wires. I didn't sort of need these things, but apparently nowadays I do. And trying to look at things like how they're adding, or looking at the fact they will add exponentially to the complexity of verifying the correct design, that sort of thing. Randomness, because apparently that's quite important for security and repeatable testing. So obviously part of what people have been talking about is verifiability and all that kind of stuff. Generally that means I'd like to know that the test cases come out with the same answer every time, not something different. I'll make some comments on resource exhaustion using mathematics as an example of the sorts of problems you get there, and also converging a system to a quiescent state. So trying to look at the sorts of things that come out of these things, and looking at the fact that things are data driven, and you know, how that might go through. I'll put the conclusions on the end there so that you can fall asleep now and digest your lunch. There's no tests on the intervening slides. But if that's what you came for, we're in good shape. So I'll go through some general things here. So generally speaking, this is what we do when we verify security. We have a basic strategy. We defend trusted cores, restrict access, analyze in depth. I've heard a lot of talks about how we analyze things in depth during today. We want to be able to withstand prolonged sieges by determined attackers. We have strong points. We have inter-strong point lines here. These are the ammunition tunnels in the Maginot Line there. You'll see that I'm putting up a set of successful designs here. And as a French company, obviously, I'm doing that with the Maginot Line as well, so I apologise to my employer. And we want proactive attacks against threats and things, so actually to be much more responsive to what we're doing. Clearly that's what we did in the Middle Ages and up to the Maginot Line, so we wouldn't do that kind of stuff now. Actually, that's not true. That's exactly what we still do now. We analyse things into different ASIL cases on cards. This is exactly what we still do. So really, from my point of view, the question on the complexity thing is that actually something that viably has some chance of delivering you a verification solution, or are you sort of whistling in the wind here? And my view, he says, as you'll tell from the language, is you're sort of whistling in the wind when you try and do that, and probably we need to look at different things. This is a hugely complex slide. It's generally designed to frame the bits in the middle, which are the bits that people variously talk about when they talk about security. They talk about things like signatures, encryption, roots of trust, all this kind of stuff. They very seldom talk about what it's actually being used for, or the fact that that's merely a useful tool that is being used to achieve the security. So to me, this is a much more fundamental thing. You can tell by the colours that I'm colour-blind, incidentally, so if it's offending anybody. Security is not a useful concept. It's much more normal to speak of the certainty with which a desired characteristic is achieved. I think that's really quite important. You know, nobody buys a system to do security. I like to say my job is to be a parasite. I work on actually trying to provide things to other things, not security for its own end. And that's a really important thing to concentrate on, because what you'll hear and what you see in the press is people talking about systems that are secure. And I have no idea what that means. And I've been doing this for 34 years, so I should have learned that by now. So I haven't. So you're welcome to tell me at the end of this, but not during my talk. So I put a sort of set of questions there that goes with this thing. So what does it mean when you apply your signature, for instance, to third-party card? It's much more to do with what these things mean than it's to do with the fact that it's a signature. Or if you did that separately, what does it mean when one third-party application denies access to another by using signatures, by using whatever? Yeah, that's a security thing, isn't it? You want availability out of this stuff. What happens when one of your clients' root of trust is hacked? So when you're talking at a system level, when you're talking about the security that goes into these things, these are the sorts of things that you're expected to have, or you should have, some kind of an answer to. So that sort of posed the question, if that's the one you thought you were here to listen to. This is why I think security is the enemy of verifiability, because you actually have to look at a lot of these things. You don't need to just know what the mechanism is. So anybody that equates security with the mechanism is essentially simplifying the issues that they have to deal with on this one. I've put this one up. If anybody's heard me talk before, they may have seen this. I've got to even more garish colours here, I understand. What this is designed to do is to actually talk about cyber security. So actually to give you some indication that actually what you're looking at is not just those things that are to do with did I design it correctly, did I code it correctly, did I do all of those sorts of things, but the sorts of things that you'd be hearing if you were across the road, yeah, in the other room there, of actually somebody's now deliberately attacking this instead of actually waiting for things to fail in a normal way, in which case maybe it would come out sort of once every 5 million years. They're deliberately doing these things against me on my system, and this is what security is supposed to be defending me about. So when we talked about the fact you cannot deliver digital advantage increasingly without the security, this is what it means. You have to counter these sorts of things, otherwise you don't really have a system. What I've tried to do here is to actually set out one of the other things that I think is important, namely that very often systems will be operating, and a single system will be operating in a way that that is actually designed to achieve multiple objectives simultaneously. So, for instance, it's got safety. If that's me, I'll shut it up. It's got safety. So, and I've tried to set this out in terms of the type of evidence that you would be providing, because it's not always the same evidence. But one of the things that's important there, I pretty much want to monitor any safety system I have. I don't like encryption when I'm doing safety systems. Yeah, I have no idea how to do these things properly. When I'm doing data protection, I almost always want to encrypt things. And I actually care about things like data minimization and, yeah, and where I am located as part of my security solution. And I have different people who will take me to court and expect different types of evidence that go with those things. And most significantly for me, and it goes for the Internet of Things and all the rest of the things that were just being talked about on the previous discussion, people expect to make money from the data they have in their systems. Increasingly, that's how you pay for the systems that we have. Now, in order to do that, pretty much, if I haven't encrypted it, you've already got it. So it's very hard to charge for things that you haven't secured. So in certain circumstances, I'm able to arrange for these things all to be on separate systems, because we knew how to separate them previously. However, my observation on, for instance, the automotive systems going forward, healthcare systems, most systems that I'm looking at nowadays, this is actually data that's occurring on the same system. So when you're talking about verifiability of my system, I'm talking about the fact that the security is being used to deliberately obstruct certain of the functionality that you're looking at. And before lunch, somebody interestingly asked a question about conflicting requirements. If I look at each of the individual systems that are running on this, I may not have conflicting requirements. If I look at what has to run over my infrastructure, and it's increasingly true that I have not developed an infrastructure to do this, then actually what you're getting is very heavily conflicted requirements. So that's got to my summary of what the problem is. Yeah, and not everybody has fallen asleep, so that's very nice. So my problem is looking at what do I actually mean. So I've tried to bring this down to some much smaller problems on what sort of thing that you're looking at when you're actually looking at security and how it emerges into systems. So generally when I'm doing verification, and bearing in mind that that's what I was looking at, so you're at least halfway through listening to me. I'm looking for things that are deterministic, repeatable and tested. So I want to be able to test these things and verify that it's doing what I want to do. And that's great. So when I do security systems, one of my most important concepts is random numbers and randomness. If I'm going to encrypt something, I like it not to come out the same way each time, because otherwise that's bad, or at least if I encrypt it with the same key. But essentially, what you're looking at is systems that come out differently. And they need to be true. And if it's not, then you're actually not testing the system very often. You test one use case on the system. And you'll almost certainly be getting different data, signature and hashes every single time that you're looking at this. So things that actually were easy to test previously because it was an open system become much harder to test because I'm looking at things that differ all the time. And they're designed to do that. And if you're not testing that as part of the characteristic, you're actually not verifying the system because that's part of what you're actually concerned about. Very often I'm looking at things where you're now using data as signals. We hear about this a lot. You're using data as signals instead of using physical lines and things as signals. And we learnt this previously when we were trying to do formal methods and we had certain formal tools. It's very hard to do data-driven things. I can do signals that go backwards and forwards and make sure that I can validate that. But when I'm looking at something that's got 256 different combinations for every 8 bits of data that I'm passing down there and only some of them are right, that's actually got quite difficult to actually validate I'm doing the right thing. So if that's what's emerging as part of the perimeter of your element that's under test, that's a pretty difficult thing to test. And none of these things have system significance. So the stuff I'm talking about in terms of the mechanisms and things actually is not something I recognise at a high level. I recognise other objectives like am I doing data protection or am I doing safety or am I doing whatever. I don't recognise these as part of the objective I'm trying to achieve. I recognise them as tools I'm trying to use in order to do that. So for some of the things you get there, you've got the real questions that you're trying to ask around the randomness that says, do you or do you not use your cryptography correctly in order to achieve this stuff? This is a fundamental question you're asking at the level of verification. Because using your cryptography incorrectly will almost certainly be blocking other systems aspects that you're after. So it'll verify correctly for one thing and stop a whole bunch of other things from working. So it'll quickly balloon the complexity. And do you test the system correctly? Let me come on to another couple of examples here. Resource exhaustion. I did a bit of maths underneath that, but I got rid of it because I would never go through it. So things like public key, the sort of things you might use for quantum replacements of that are extremely mathematically and resource intensive. They often have very tight loops that you go through in order to achieve these things, or they use accelerators to do these things, which is great. So from a digital point of view, I can sit there and I can work it all out, that actually these things are highly optimized and they go through and it does what I want it to do from a verification point of view. The interesting thing is, if I have a key that's one bit too long and I'm trying to generate it and it doesn't fit in the accelerator that you were using for that, it has an order of magnitude 100 times, or at least potentially has an order of magnitude 100 times implication on the amount of resource it will consume, which is going to stop other parts of your system working unless you've very carefully designed it to make sure that isn't true. So when you're saying you're putting security in there, all sorts of resource exhaustion things are going to become part of what you're looking at, and they're going to be driven by the data. So we talk about the code and we analyze the code and we do all those sorts, but it's actually the data that's going to be changing the performance of what you're doing, and it's that you need to be verifying. Hyper-connected systems. I apologize for that. I'm sure I must have got it somewhere. I can't possibly have generated something that inane. Or perhaps I did, in which case it's copyright. But the whole point about this is, we increasingly, in fact, you heard it in the previous talk from Cadence, we are not part of an individual distinct system anymore. We have to fit into these extremely connected systems, which I know nothing about in many cases, but I have to fit there. So the sort of questions that you're asking in these sorts of areas are, If you were trying to exchange public keys, so I've got 1,000 public keys I'm trying to exchange in an extremely cluttered environment with people I didn't know. It's not the public key bit, I've tested and verified that. It's the fact that only 1% of these things are getting across without being fragmented. So the design of the system so that you actually know what you're doing in relation to that when they fail is actually going to be a much more important thing than the simple did I exchange keys and things of that nature. And I've yet to find people properly considering that that is part of the consideration of their security thing. They are making statements, and the reason they're using the mathematics is because it allows them to make statements with a certainty that comes from the maths, but without actually considering that they actually can't make that statement at all because it doesn't come from the system that they're putting these things into. So it's extremely important there that you're looking at things like remediation and what are you able to do and what are you going to do when you haven't exchanged these things. Because I presume you put the security in for a reason and it's not succeeding in exchanging. This element about verifying the systems, in fact providing the correct data and the signals that go with that, you become much more sensitive to actually running on the same width of things, so 8 bits of data. If you move to a 64-bit processor for an 8-bit one, I've suddenly got lots of different variables I can do. It's not the same in terms of these things. And you get different capabilities. So signals used to be just a digital signal. So I'll do this. What is your verification strategy for decrypting these things? What happens when it comes out wrong? Because my attack against you, I have to say, is to make sure you get the wrong answer. Yeah, the nice thing about security is that you only get the right answer in one case. The really bad thing from verification is you only get the right answer in one case and you have to account for what you've done in all the others. So how are you going to run the system? So except in a simple case when your answer is, I'm going to turn it off. Yeah, this isn't really an option to go forward on these things. So I think, he says, oops, sorry about that. I think what I wanted to do, conclusions, that was almost on time. I think what I wanted to do was actually suggest that when you're talking about security, it is really important to understand the system that you're going to go into and how you want to verify that. Not to pretend that you can actually get extra things and to recognize that it will massively increase the complexity of your analysis to get a verified system. And I suggest that in most cases it will mean that you conclude that you're not able to do the type of verification that we've traditionally done in things like the avionics industry and things like that. It will mean that you're looking for a different strategy. And certainly in our case, we're looking for a different strategy.
Thank you. You can tell us what the strategy is?
So our strategy, yeah, I can tell you. Our strategy is we are looking for diversity in software for things of this nature so that we don't get common mode failures.
Okay.
Yeah, so actually a lot of what you've looked at going up until now has been, yeah, I concentrate, yeah, for verification purposes, I concentrate on getting everything to turn out the same. That means as a cyber attack, I can now go through those things, marshal my attack and get them all to fail simultaneously. Thank you very much. And I can get pretty much universal failure across the world if I want to. I am increasingly looking at, I have to introduce difference somehow into these sorts of things. Otherwise, I don't have a verification strategy that will give me certainty around these things.
Thank you very much. You got the answer as well. We do have time for a question or two, if you have a question or two on that topic. Martin. Do you want to introduce yourself?
Yeah. Martin Lampard from Cadence. You mentioned you tried formal techniques or formal tools. In what sort of application areas? Hardware, software, both?
So we do combined systems. They're distributed communication systems largely. And in fact, they're mostly high assurance communication systems of one sort or another. And the observational, what we went for the tools when we could actually get automatic code generation and we could get backwards and forwards fast enough that we could actually demonstrate that the model didn't actually turn out with the correct effect. So we went at that stage for doing those sorts of things. So where it's a very constrained environment and I have certain things, it is an extremely useful tool for removing logic errors. Yeah, so I don't get logical failures, but doesn't give me any proof against resource exhaustions. It doesn't give me proof against other types of failures I get in my system. So it's not that I would say it's not a useful technique. However, it is increasingly not a technique that I can scale to the areas that we're in. And as I said, the more it went for things that were data driven. So where we were doing key exchanges, I can do the signals that go with a key exchange, but I can't accurately analyze all aspects of how things would change, when in fact what I'm trying to do is change all the content of it.
Hi, Andy from Cirrus again. So this is interesting from a verification side, but it's probably an even bigger challenge from customer returns and in-field errors. Do you have an approach to where reproducibility is the biggest issue of that? Obviously you don't have reproducibility in this because of the inherent randomness of the encryption. Do you have an approach for that as well?
Clearly, or it may not be obvious, I come from the part of the company that sells encryption. So basically, if I avoid the glib comment that nobody buys an encryptor and wants to ever give the piece of kit back to me, they do want to know why things go wrong, and they want to know what's happening in relation to that. So in those instances, it concentrates on where security is actually a positive aspect that they're looking for. So they're looking for the ability to generate keys or things of that nature. That is a testable thing, and we have logs and audit trails and things that go with that, which is very important. And we are able to demonstrate as part of the testing that the mechanisms are being correctly implemented. When we go for actually putting things into systems, the audit trails that go with the systems are much more important. We're generally able to demonstrate why it's more of a forensics thing of actually demonstrating why they have not used it in a way you would have expected. Or that they have, but I mean, so one obvious answer is you get people getting random number failures. Well, okay, if it didn't get the failure every now and again, it wouldn't be a random number. You know, here's the textbook, have a read, and that sort of stuff. But actually, it's much more a system-wide set of things that we go through, and generally speaking, the fact that we're actually talking about the right sorts of things as opposed to pretending we can do things that we can't is appreciated by the customers.
Last question.
Hi, Dennis Neckel. When I go to cybersecurity meetings, there tends to be a lot of emphasis on modelling the threat before making any attempt to verify against it. In your case, you're suggesting, well, putting forward the idea of introducing variability into the system to prevent large-scale common mode failures. I can see some environments, such as critical national infrastructure, where that might be very sensible and appropriate for the nature of the failures. But certainly in some military applications, for example, there's the situation where any single failure is as bad as a catastrophic failure of everything. And if you're building a dam, it doesn't really matter if all of it falls down compared to just one large hole.
So in talking about that and talking about modelling so you could get differences, you're right, you talk about that. But one of the things that was on that very complicated slide with the garish colours was the suggestion that we don't know how to numericise attacks and things in relation to cyber security. One of the things that I think I have to find a way to do is to do the same thing that my colleagues on the safety side have done. I've got to get to a situation where I don't get to attack this over here, this here, and this here, which were three separate mechanisms that stopped my dam falling down, and then bring those together in a single attack on this. So I need to make sure that these things act serially, not act simultaneously. So the only technique that I believe that we actually have to try and get some level of assurance is this idea that we don't get things failing, you know, we don't get a concept that I can never make this fail. What we have is a concept that I can't make these things fail simultaneously. The problem I get with cyber attacks, and the problem that really people should be talking about in relation to that, is I convert what would have been a 10 to the minus 9 to a 10 to the minus 0 because I managed to put them all in one place. But I also have global scale with that. If I can use things like open source software, or I can use things of this nature, and I can find it everywhere, then I can actually make that happen everywhere. And I don't have to learn, I don't have to learn my attack, in the place where I'm looking. So I think that it's one of the few techniques. I wasn't suggesting it's the only one, but I think it's one of the few techniques that we understand that we could start to apply. And the reason for suggesting it is The general direction of verification is to push everything towards everything works in the same way. I'm suggesting if we continue to do that, we're actually making our situation worse. We have to get variability and look at the consequence of the failure rather than the fact that there is a failure. That was a very long answer, I apologise.
Right, thank you very much. A very interesting talk. Thank you, Peter.